Here. So welcome everybody. Thanks for staying. I don't know if a couple of people are still outside. For sure, Michael that wanted to attend my presentation too. So I must say I'm very glad for how it went this afternoon because, okay, not only for the nice fogliatella that was organized for the coffee break now, but also because I saw all the questions that were made during the first part of the tutorial, and also some of you came to me to ask some information, and this is 100% what I will present in this second part of the tutorial. So here, exactly as Gulsen was mentioning, there is like expectation is matching the content. I hope it will be exactly like this. And also was noticed this from zero to hero. This is exactly meant in a way. What I'm trying to sell here today is how to be successful with SAR in one day. Everything you need to know to get started and be successful with it. So I will have a brief introduction with all this about, so a bit what I will explain. All the examples that you have seen in the first part of the tutorial, after seeing this, you can implement by yourself. This is not a classical tutorial on basics of SAR, so we treat SAR as just one other modality. These are images, but we should just put some attention on the type of processing we do before applying machine learning. The machine learning part will be, okay, how should I deal with my data? What type of data can I get? How do I procure my data? What SAR processing I need before machine learning? And also the pre-processing to make things work. And at the end, if we have time, I will show you also some training examples. So what are common examples for some specific applications? And takeaways, of course. So this part of the tutorial will be very, very different from the first one. So I ask your help. This will be interactive. If we have issues with the microphone, I will always repeat what you say so that we also get it recorded on camera. Materials, so we will use these slides. I will show you the most common way of downloading the data, some free data that are online. I will show you some common processing that you can do. Everything is available on Snap. Google Earth will be used, so just to show you what data are matching to what. And also at the end, we also get a Jupyter notebook for something that you can simply implement before your trainings so that it's most useful as possible. Questions anytime during the lecture, just raise your hand. I will stop so that we don't lose track of all your questions. And as I said, I will not bring the microphone there. I will simply repeat what you're saying, so we are good. So, as I told you at the beginning, from zero to hero, it means, let's say, what is the successful story that we want to tell here? You want, from zero, apply some machine learning for SAR, and you find an acronym that no one has used so far, so you will talk about machine learning for SAR. So, faking that you had never heard it before. Then, is it too low? You can hear me? Okay, so it's better. Then you will have some sort of network architecture. We will fake that you didn't use the unit and you give it your own name, something fancy, possibly. Then you will have some inputs. What I'm showing here is mid-resolution data, or you can get some higher resolution data. By the way, the range resolution of the data depends on the bandwidth that you are using. Someone may ask you very soon, just for you to know that I'm not plotting formulas here. And then you can get a task you get here on top. So classification, there was a city. Someone else wants to do multi-label classification, everything in a supervised way. Someone else wants to do something more complex, so we classify every single pixel in the image, so we talk about semantic segmentation. Or we could do even something more complex. We do regression on every single pixels. Examples of these last two is the NDVI from SAR or any other type of length cover classification And here you can get, for example, again, the image to height, for example, or some other parameters, even the speckling. So the denoising of SAR data can be in this category here. Or even use few labels, no labels, and rely on some sort of self-supervision on unsupervised methods. So, but at the end, what you want to tell is that you got an accuracy of 99.8. 0.9 wouldn't be plausible, I guess, so you will stay low to reduce expectation, and then you get your work through. Whatever it is, it's your thesis, it's your paper, and so on. How do we get there? What is of realistic that we can actually do to get closest to this story? I want start from a common ground here. I would like to understand, I saw that the audience here is very diverse, and this is the nicest thing here, and also way larger than last year's. So I would like just to split the group in two. I would like the one of you that has ever have had a bit of experience with SAR, just raise your hand. So just to understand how many of you. Okay, thank you very much. So not to discriminate anybody, we will call the one with experience my favorite ones, and then the one without experience, the others. So I will ask you, let's say both groups will need to answer some questions here, and we will start exactly from that. So where should we start? I got already some questions about how do we normalize the data? Should we use the sigma, the beta, the gamma? We have seen also in part 1 of the tutorial. I would like to have a couple of feedback. So from one among you that used SAR, just what was, let's say, a difficult aspect that you faced. You came to me, so.
Difficult aspect.
I will repeat it.
I was confused where to start. What kind of polarization should I use? What kind of
Perfect. So one point I understand is what type of data should I use? And this is, let's say, one of the first aspects we will cover. And from someone without experience on SAR, I would like to know what was the first question. So if it was where to start or what should I do? Anybody? Please.
First, I didn't know what would be the difference between SAR and optical sensors. And
Excellent. Okay. So what was said here, I use optical data. Well, now I can easily download also SAR data. Why one or the other? This is also a very good point, and we will discuss this. We will also comment a little bit about the differences and every single aspect. So everybody of you, whatever is the level of experience, can get something from the presentation. So let's move on. In one slide, what are the most complex things we see? So data download. What is the data type I will need from what sensor and how to download the data, how to procure the data? Should I pay for it? Do I get them for free? How many data can I get for free? Then we have the aspect of SAR processing. So here is just a sneak view of what is happening afterwards. How do my data look like once I download them? Is it easy to then use them? Then we will see something more related to machine learning. We all know, for example, one common problem is we want to normalize our data set. How do we normalize it? How do we make this normalization work on several data sets, on several sensors, and so on? And the last part, here I put our lovely unit here, and it's about the ML training. What happened if I do some processing before? Should I take care during training about some aspect? The answer, as you may expect, is yes, definitely. The slide about SAR basics is one slide. And then, as I said, we will treat SAR images as simply +1 modality. And I recall what we have seen in part 1 of the tutorial. This is the geometry, acquisition geometry of a SAR. I would recall this, this image also afterwards. Everything you need to know here is that you get something like this, black and white. Every pixel is a complex pixel. We have an amplitude and a phase. We have seen that the amplitude for the case of one single image has way more sense than the phase. And this is everything we need to know so far for that. You need to know this is absolutely not exhaustive list of what exists and what will exist in the SAR domain. We have plenty of different satellites, and here I'm not here to explain every single details, but I just want to make you observe that some satellites look similar, some other satellites look different, and probably satellites that look similar will have also similar data, and the one that looks different probably are using some different methodology to generate the data. So this is what is existing in the first row. We have the Tandem X and the TerraSAR X that probably most of you have already heard about. Then we have an extremely similar system that is the Cosmos SkyMed. This is all, they are both working at the X-band. Then we have an L-band satellite, ALOS from JAXA, the Japanese Space Agency, and the Sentinel-1, already active from 2014, very similar shape. Very interesting. So we have an antenna, solar panels. These are the distinctive traits that tells us this is a SAR satellite. What is coming? Constellations. We put satellites before and after the Sentinel-1. We get the Harmony missions for doing some advanced processing. There is the Roselle still from ESA that will come. This is an L-band SAR. Then a very well-known ISOR that had to be launched already, but will be probably launched next, which already looks different, like with this umbrella, and this is not the only design that is this way. For example, there is also biomass, there's this paraboloid antenna, and this already suggests that they will probably use similar acquisition modalities. So when you start, you cannot really say, okay, I want that for, you should have a reason. And reasons may be very vary. So one point might be data availability. So we could spend quite some time, which is the best resolution I need, or what is the best operative band that I need for a specific application. But most of the time, we use what is available. And the Sentinel-1, thanks to the Copernicus project, is one of those satellites that provides data on a regular basis and for free. So this satellite will be for us, for now, the reference. I also believe it's the type of data that most of you are using, simply for the fact that it's free. So even if you're focusing on a different band, then sooner or later you will resort to Sentinel-1. Why not to look what is happening at the C-band? So this is a C-band instrument. We have several acquisition modes. So the one you were using probably, you should know, is not the only one. It's able to perform interferometry. I'm not saying a single word about interferometry, and this really hurts me, but we are focusing on different things right now. Then we have two polarizations available, VV and VH. Meaning that we send in a given polarization, receiving in the same polarization, sending in vertical polarization, receiving in horizontal. I also will not spend too many words. We could discuss afterwards about what that means. We have two satellites, so we get a revisit time of, for two satellites of 6 days. Very, very nice for many applications. And furthermore, it's a mission that whose continuity is assured from the fact that even if we have only two satellites, we are sending in the space more and more so to have continuity above the time life of a single satellite. I mentioned a little bit acquisition modes. Let's see what this means. And especially, this is especially interesting because Sentinel-1 is able of doing almost all of them, of using the most common acquisition modes available. So we have the primitive, the pioneering, the primitive mode, acquisition mode, that is the strip map. So this is the simple SAR. So we know the SAR is flying, is acquiring in a straight direction, and we get Usually at the bands we are working, X band, C band, relatively, even at L band, relatively mid to high resolution. So they are relatively sharp images. This is used for science, but also a lot for surveillance. A lot of private companies are getting into the sector and using this modality. TerraSAR-X and TandemX were working mainly in this mode. Then probably you have already heard about ISAI, Capella. Here we can add also Umbra. This is a mode that will be always present there. Apart then on top they will do some spotlight and increase the resolution as much as possible. So this data will be mainly commercial, but there are always free options for research. Then we have the ScanSAR and the TopSAR, and specifically the TopSAR is the acquisition mode, the main acquisition mode of Sentinel-1. And what is happening here is that while the satellite is flying, then it's looking in other position on the ground. So most of you probably has used this data without knowing that we want to increase the SWOT, and that's why while I'm flying in this direction, then I also look at other SWOTs just to increase my SWOT, and then that's why we can achieve a revisit time of 6 days with 2 satellites. Of course, what we decrease is the resolution. So we can increase coverage, but then the resolution will be coarser. And the type of applications, then commercial applications probably will not be possible. I mean, surveillance application will not be possible at a lower resolution, but still very important and crucial for science. This is examples using the TopSAR mode, this Sentinel-1, Roselle and Biomass. We use ScanSAR. Yeah, and most of the data, basically all the data will be open, freely distributed. A video will explain the thing way better. So the Sentinel-1, this is what it's doing while flying. So with the goal of increasing the coverage, so we have 3 times the normal coverage of a strip map. At the cost of resolution, we can generate much bigger images. And then we have, of course, several different applications that are possible. It looks like a nice thing. This is sure. But this is how data look like when you download them. And I was one of you, like I was opening the data and was saying, oh, wait a second, I see black intervals between my images, and then I have also the repetition of some pixels here, because this has a given overlap between the different little tiny images, which we call bursts. And then every single SWOT is called a sub-SWOT. And then the full image, we talk about SWOT, okay? So this just to give you some terminology. This was the flight direction. Then we will need some operation like the bursting and mosaicing to get the actual image. Already this operation is not the easiest thing to do by yourself. So you will need the support of some processing. And I will show you afterwards how can you do this with SNAP. Now, if you believe that this is the worst that can happen to you with this type of data, this is not. There is something way more complex happening for the only fact that we wanted to increase the coverage. Now, the thing is that you should not be 100% aware about this when you want to do your machine learning application, but someone sooner or later should tell you that this is what happened when you acquired one burst with this sweep during the burst. So you get, I will show you what you get soon. So this is the strip map mode, and we have a frequency time diagram. And basically, this is all your image. The time is basically aligned with the direction of the flight. So what we call azimuth in SAR images is aligned to this line here, and in this direction we will have the basically Fourier transform of our range line. And what we get here is that this has no, this is basically the bandwidth of our signal. When we have a movement towards back and forth following our flight path, we get something that looks like this. It looks super complex now. Let's understand this. So this is the unfocused data. After focusing, you get this gray line here, meaning that the first range line and the last range line have frequency modulation. So this is just for you to know that sooner or later you will encounter this frequency demodulation in this type of data before doing any type of operation. And this may even happen when you want to split your data for machine learning in real and imaginary part. This is the cause on which you have to do some additional pre-processing. Otherwise, your machine learning algorithm that you were training on stream map data, for example, so on something that looks like this in frequency, applied to TOPS data will not work. And so you should know why. So just keep in the back of your head, TOPS and ScanSAR have frequency modulated burst, which usually has been taken care from Snap for whatever operation you want to do. Okay, so from now on, everything will be way easier. So this is the deramping. So a frequency modulated signal should be brought in the baseband. So we do a deramping, so a demodulation. We have that all the range lines are in the same bandwidth. And then we do some type of processing, and then we re-ramp our data to say, okay, I did the processing, now the data is like the original, but probably I removed the noise, or I did some other operation. Okay. From now on, as I promised, will be everything way easier and smoother. So let's start with data procurement. What data should I get? So we saw that we have different missions. We have national missions that often offers free data, but in case of TerraSAR-X, for example, we need to pay the data, or we get a tiny bit of the data available. Of course, this is nice for prototyping, and the situation is way better than 10 years ago, that's sure. But at the same time, if you want to generalize worldwide, which is a big issue in machine learning, now you need more data to test, and not always you can get it in the region at the time that you want them. Of course, we have private companies, the same logic applies. We have new free and open data policies led by ESA, and actually ESA was pioneering this with the Copernicus program and Sentinel-1. Basically, we have worldwide data with a nice revisit. So it's a nice tool we can play with. And then additionally, ESA is also working as a hub to store the data and to provide data to people. And this can be, for example, from TerraSAR-X and Tandem, or the ALOS data. ALOS2, I believe, is possible to download. ICEYE, part of ICEYE data are possible to download. So there's plenty of option. And then Google play also here a big role. I guess plenty of you download the data from the Google Earth engine. And even here, you get something that, so you wanted something, you want some SAR data, and then you got GRD. Now why GRD? Now where is this GRD from? Then you should look it up, what was the processing that was done, and then you should get, okay, what have all that done without it? What if the GRD, I'm downloading it from the official website of ESA? And these are, again, two different things. And we will understand this one too. So data download, officially, the first web page that one can suggest you is to go on a browser data space Copernicus. This is a new website, and you can download basically all the data you want from here. Usually, these are only the most recent data that have a fast download. I believe most of the data are archived. So you will send a request, and then you will get a link to download. I believe nowadays it's still like this. You get an interface where you could select the sensor you want, acquisition mode, the days of the acquisition, and also the orbit. We will see now together, I will show you how to download the data and what you have to take care most. There is an alternative to this. It's a nice alternative provided by the Alaska Satellite Facility, which works also very, very smooth. We will not see today how to download the data, but also works very intuitively. You will need the following account on URS Earth data, nasa.gov, and also on Earth data, nasa.gov. And yeah, this will also work very smoothly. So I will show you now. I will leave the slide. I hope I will not lose you, that I will be sitting. So you can see it. Of course not. Let's see. If I do like this, it's working fine. Perfect. So very, very briefly, what we want to do here is like we want to search for our data. We want, of course, the Sentinel one. And then we see that already here we have several options. We can download raw data. We can download single look complex, GRD data, and some other higher level data. So for now we say, okay, I want to go for Sentinel-1 single look complex, which is the actual SAR data. Then you had the possibility to define a given area. For example, and without a mouse, this thing is not working properly. Okay. So we could go on Benevento. And the network is relatively slow, so of course we will not download the data now. I pre-download them, and also they are already also on Snap for later. So you have the possibility here to define your region of interest. And we need to do this, otherwise I cannot show you. And then we have some filters. So we have the possibility to download from 2 platforms. As you know, in this right moment, we have only Sentinel-1A working. Sentinel-1B is not working currently. Then you have the possibility of selecting ascending orbit and descending. I'm not explaining here what this exactly means, but we can talk about it afterwards. Then we have the acquisition mode. So SM stands for strip map, and IW stands for interferometric wide swath, which is the same name for TOPS acquisition mode. So this is the most common data on land, so we will select this one. And then we have other possibilities. We can select what polarization we want, but as I told you, the interferometric wide swath is mainly these 2 polarization, so we don't select anything here. And we select the product availability immediate. I guess here at the end we get the latest dates. So let's go from some days before, and let's see what data we get. I zoom out a little bit. So what you see here is a preview of what is the swath of Sentinel-1 data. So this area that I selected appears in this swath here, in this other swath here, and in this other, in a third swath here. So could anybody of you tell me what is the difference between this swath and this other swath? So they are not matching the direction. So you raise your hands. Perfect. So the answer was that since we have a satellite going through the poles, we have 2 possibilities. Rather, we can acquire while we are traveling from the south to the north, or the other way around. So of course we have that the orbit is slightly disaligned from the vertical line that goes through the Earth. And that's why we have this slight different inclination. So it's not exactly passing through the north and the south pole. Therefore, so one is equivalent to the other. We could even use them both to increase our the sampling of our time series. We can select one, and then I show you. So here, when you click on it, you get several data, all that refer to the acquisition interval. It is shown how many images you get in that acquisition interval. And interesting part, so in the name you also get the date, like this was the 9th September, the 28th of August, and so on. And the nice part here is that in this eye symbol you get some info. You get a quick look image, so more or less how does it look like. And if you want to download, what if you want to download exactly the same SWOT even in a year? So how can you know what you downloaded? It's very important to look for the details of your acquisition. So if you go in product, one very important parameter here is not only that this is an ascending, but once you know your region of interest, you should look for the orbit number. It's the relative orbit number, yes, which is now the 44. And I say that because when you want to do, it's not only for downloading exactly the same SWOT and to make a time series, but for example, plenty of you have mentioned before to me interferometry and interferometric applications. In that case, you cannot simply take two images that overlap, but you should select data from the same orbit. We can discuss this as well afterwards if this is of interest. So now I will not take longer for this. You click on download, you wait a bit, and then you start with your application. So I believe here is not. It worked, fantastic. So is there any question so far for the data download? Okay, I guess for now we are good to go. So next topic will be what data I need. Do I need to do some pre-processing and so on? Yes, a lot of it, as you can expect. I recall again the SAR geometry, acquisition geometry. So we have a side-looking system. We have a system that acquires several pulses to form an image. We have something that has a statistic that is not Gaussian. We saw in the first part of the tutorial. So we have plenty of characteristics of SAR data that we should take into account. Let's say the most important three are depicted here. You have spatial properties to take into account, so how your data actually look like. Is there any deformation in your data? Does it look like as an optical image or not? There are some radiometric properties, so it's not only the shape of my data, but how bright is my pixel actually. And this is actually something, it's a physical measure, the SAR. So we should understand how to get that physical measure. What is more physical related and more to simple normalization. So we will get to explain this too. And then statistical properties, we should never forget about the speckle. We will see what this will imply towards the end. So let's just have some fun with images. So to slow down a bit on concepts and let's visualize. So this is the, do you have enough, is this enough bright? Yeah, this is the maximum. So what you are seeing here is a spot in Indonesia. This is the Mount Bromo. And I'll show you the comparison, as you asked before, what is optical, what is SAR. We have, here you can look at probably better, you can see it better here. So this is the optical one, this is the SAR. Nice, they look similar, that's very nice. But still, there are very different features in the data. So what do you notice? What is the main difference that you notice between the two? One hand up, please, not all together. You? Very nice. So the first answer is there is a rotation of the image. This is of course true. We have one image which is probably in lat-long coordinate, latitude, longitude coordinate, probably even orthorectified, and SAR it's not. SAR is in a completely different geometry, which is the SAR geometry, which we also call slant range azimuth. These are the two directions. Then what else? I saw plenty of hands. Please. Very good, very good. So another thing is the geometry of the scene, like slopes appear differently in SAR and optical, but we will see that, and I will mention exactly these effects that you were mentioning. Somewhere on the back, in the back?
Change of the blackness based on the slope.
Okay, so it was a similar answer. Okay, very good. Anybody else wants to? Yes.
SAR image is grayscale, I think.
Mm-hmm.
Optical image is RGB.
Very nice. So we can say directly that optical is acquiring in a different way. So we have different channels. We see colors, which bring way more information. In a way, instead with SAR, we have black and white. And somewhere there also raised their hands. Okay, it was the same. Okay. So this is all correct. Now we try to understand why and what this means, and what information we can get out of it, because then otherwise, okay, optical is good, then why do we want to use SAR in the first place? So let's just focus on this area here. This is the Mount Bromo again. This was in the optical image, and this is what looks in SAR. So if we go back and forth, we notice that I tried more or less by hand to align the two images so that the two circles look similar, so that the extent of the base of this mountain looks similar. So this is very, this is not the best way to align images. So there are better ways. But this is just to say, look the proportion between these circles and the inner circle. So while before you more or less have the inner circle aligned more or less in the center of the outer circle, in SAR you don't have this anymore. And this is basically due to the fact that slopes look different, targets that are at a different altitude look positioned in a different place. And this is also the principle why the image to height from SAR works. So we are using exactly this information. This circle moved in another position, then it means the altitude of this inner circle is higher than the base, okay? So let's try to understand with a bit of geometry why this happened. So this is the actual geometry, so what we have on ground. And this is just to explain you, so we have a regular pattern here, a regular grid, and then we have a line and a circle. What will be visualized from SAR is that the point of the grid close to the sensor, what we also call near range, will look closer to each other, and then farther away from the sensor, they will look farther away. And this is a direct consequence on this side look geometry of SAR. Additionally, and actually as a consequence, since the grid is not regular anymore, we have that the line also is deformed as well as the circle, okay? So as your colleague was mentioning before, we have a name for this effect. So if we have a positive slope that is looking the SAR sensor, this slope will look shorter. So, and this is it's very simple to observe in ground range. So on the ground, the 2 points A and B are at a given distance. In the sensor, in the image, they will transform in A first and B first that are much, much closer. And as an additional effect, we also get shadow because we have an area that we are not able to visualize at all. Another effect is what was also explained before, is the layover. So when the tip of a mountain, so the slope is so high that the tip of the mountain appears before the bottom of the mountain. So A and B are again, A is on the left, B is on the right, at a given distance. They will look the other way around in the image. First B first will be visualized, and then A first. I will show you in a moment how this looks like in an image, so we can explain a bit better what we were observing before. So here, this thing that looks brighter, it was a slope, which compressed in less pixels. Can you also tell me why it looks brighter? Please, Felix. Of course, it's because of the incidence angle. It is incidence angle dependent. But why it is brighter, please?
Because the feature is acting towards the sensor.
Mm-hmm.
So when the pulse of the radar hit the ground of that feature, the reflectance or the return from the sensor is the first one.
Okay, this is also a reason, like you have a geometry that is scattering more power in the back, but there is a direct reason. Is there anybody else, please?
Maybe it's because on a slant range we have left with a small area to register all this energy, so they sum up together.
Very nice. So the answer, the main reason is that basically in a smaller area you are summing up the same energy. The brightness of the pixel is going up. So, of course, everything you also said before, it's correct, and we will see also that this type of effect can be compensated exactly considering the local incidence angle. So we see this here, but we also see this on the side of the mountain. Let's change a bit scene, and let's see how this looks like in an urban scenario. So here we have skyscrapers, big tall buildings, probably not even skyscrapers, but mainly tall buildings. And then we can see exactly what we said before. We have a layover effect. So this is the top of the building, which appears before the bottom. Can any one of you guess from which direction was this image acquired? You can tell me from the top, bottom, left, right. So you say from the left. Anybody else? From the? From the top, you are saying? Anybody saying something different? Please. Okay, so you say from the right. The closest answer, of course, rather can be the right or the left, because we see that the targets align with the direction the SAR sensor is looking, and the right answer is that it's looking from the right. And the reason is mainly looking from the right, the top of the building will go towards the sensor, as we showed before in the geometry. Any question? Okay, so how do we correct that? So if we have a slope that looks smaller, how do we bring the SAR image on a latitude-longitude grid? So the first aspect that I told you, we have spatial characteristics that we then want to correct, because if we want to compare a SAR image and align it with an optical image, then we need to correct it. This process, so this is the SAR image after the pre-processing of day bursting I showed you before. This you can do it with Snap. You have a slant range azimuth grid. So this is the name of the two direction of SAR. With the operation of geocoding, also known as terrain correction, you can bring this image in something that is closer to what you know, in for example, a latitude-longitude grid. Here also makes sense to show you what is the north, because now we have proper coordinates. Can anybody of you explain what happened here? Because the two images look slightly different. Please.
We actually converted from the radar coordinates
From radar coordinate to ground coordinate, okay.
and that's
Mm-hmm.
in the SAR, there is no image or sampling acquisition. It's actually sitting where actually they are on the ground.
Perfect. So the answer is knowing the position of the satellite and knowing basically all the conditions in which we acquired, we can take pixel by pixel and precisely position it on the Earth. But here I wanted a more direct answer to why this is flipped. If this is the actual geometry, why my image looks the other way around? Please.
The last one is how the satellite sees when it passes over the area, and it's in the image matrix of how it's recorded on a sensor. And this one is the reference for us to see the north out on a globe or on a map this way.
Very good. So what your colleague is saying is that this depends from, again, the direction the image was acquired. In this case, this is the actual geometry. We have the satellite passing in this direction here. And that's why in the image, if we consider the beginning of the SAR image on the left, like if we treat it as a matrix, then we will have that the first pixels will be related to the pixels closest to the satellite. So for the only fact that this was acquired from the right, we have this flip with respect to the actual geometry. So this is just to tell you, these are all examples to tell you that what you are downloading then will need some pre-processing before that you can use it, okay? Now a very interesting thing. So we could say, okay, we are all set. We do the geocoding and then we can start our machine learning. But we mentioned before that plenty of people simply for reason of data availability are downloading the data from Google Earth Engine, right? So, okay, I'm supposed to show you how this looks like on Google Earth. Probably if you want to see it towards the end, because I believe we will not have that much time to complete this. But this is the only thing to say is that you can overlap. You can take Google Earth Pro and from a KML will be basically plotted on the Google Earth, and you will see a total match. You can add transparency, so you can nicely adjust your image to, let's say, visual interpretation, for visual interpretation. So I was mentioning the data you download from Google Earth Engine, or for simplicity, you say, wait, we download single look complex, but I have the option of downloading GRD data, which some of you already know what it is. It's basically ground range detected. Plenty of you also have already experienced using them. We have only amplitude data, so no complex data, way easier, nice. So let's use them. But what most people do is that, okay, they mistaken this type of data as a geocoded version of our single look complex, something like ready-made to be used in our applications, which is not. And now I'm showing you what is the difference. So we said this is again our image in our slant range azimuth coordinate. And our grid, the grid of our image, is linear in SAR coordinate. So we have a uniform sampling in the direction the satellite is looking. When we consider a ground range detected, the only operation which is applied to this image here is that we convert this linear sampling to a non-linear sampling, which depends on the angle we are looking at the scene. So we have a projection from the slant range coordinate to the ground range. So we have, if you can notice from these two images, more or less, so they have the same length here, including this black stripe here, but you see that the terrain here looks much shorter. This is way closer what is the actual geometry, but it's not geocoded at all. So in one direction we have the ground range vector, in the other direction we have the azimuth. If you want to geocode this image, you can do it in Snap, but again, terrain correction and so on. So it's not an easier way to process your data to go with a GRD. Is there any question so far about GRD, spatial correction, spatial characteristics? Okay, so we will proceed with a new topic. We said the second bullet point was the radiometric characteristics. So why my pixels are so bright? So what is influencing this? And again, I start with an image, just an example, and I want your inputs. What is the difference between these two images? This is exactly the same area. We process them a little bit to correct the amplitude of these two images. What is the difference between the two? Can anybody guess? Just guessing. I will wait a little bit if also someone else wants to provide answer, but thank you very much. Please.
They use the slope layer to cancel the effect of the heights of the frame.
Very good. So the answer of your colleague is that they use the incidence angle, so they use all this information about the slopes, so they know a digital elevation model to understand why a pixel is brighter than the other. So exactly what we said before, the slope will influence, because of the foreshortening, will influence the brightness of our pixel. So we can reuse this information and simply compensate it. Now, the thing is that it doesn't exist one way to do it, and there is plenty of people that studied the problem, and also this thing happened in years. So sooner or later, someone has to collect all the things, and the nice part is that researchers, scientists also, they do their job, and they say, I looked at the next mission, you should treat the data. So once you acquire the data, you should tell your ground segment to prepare the data in this given way, because then I want to download them and do my applications. And this happened really among years 20, 30. So we should understand what we got as heritage from all these years of research. And nicely, we get Sentinel-1, which is a nice playground to understand all these things. So just to tell you what this thing was, this is a Sigma node. You have already seen it in the first part of the tutorial with terrain correction. So terrain correction is geocoding. We simply place pixel in the right place. So keep this in mind. The one on the right is, of course, terrain corrected. So we apply the same operation, but on top we apply terrain flattening. Now again, since there are 20, 30 years of research, names are vary for same things. Geocoding, terrain correction, then we call radiometric terrain correction the terrain flattening plus terrain correction. This is simply, it's not that people are confused about it, it's simply that it took time to define the names. So things were called differently in different papers. So now we need to put some order. We said that the brightness of a pixel may have a physical meaning, but we want to get there. So it's not the first thing that we will get in our data. So I spared you the radar equation. So, but from the radar equation, we have that this sigma, which is exactly, this is a close relative of the sigma node I'm presenting you afterwards, and this quantity that you have plenty of times heard about. It is basically called radar cross-section, and this is a property of the target, and it is explaining in each direction I can look my target, how the target is reflecting back my electromagnetic wave. This is again as different names because SAR was not the first application where people used the radar cross-section. But this was mainly characterizing any type of scatterers, like very typical airplanes, since radar has born mainly in the military sector. So you have this radar cross-section, which is the closest thing to the physical parameter that you can get of your target. And the reason is because targets with a different shape, with a different dielectric constant, with a different roughness, will have a different radar cross-section. So from this parameter here, you can actually characterize your target. Then we often talk about the sigma naught, which is the normalized version of the radar cross-section. And the normalization is for a given area, which is my observed area. Now this will be clear in a moment, even more clear in a moment. Let's take this geometry here. So to put things in order, we said we talk about sigma, but we can talk about the beta, we can talk about the gamma. And someone of you before even asked a question, should I use the sigma or the gamma? I expect from you to tell me what is the geometry. So it's a beta geometry, sigma or a gamma, which is observed by the SAR sensor. Looking at this image here, so the area related to the beta is the black one. Then we have this gray one here on the ground, which is the sigma. And then we have this other area here, which is the gamma. So what is the SAR, the first thing that SAR sees? So we have our image, we acquire our image, we download the data, we see the brightness. What is that we are getting? You can guess, but then I also want the motivation. I got one answer here. Gamma, it is not. I know that you know. Let's see, someone else was guessing. Green shirt. You say the sigma, and also the sigma is not. So by exclusion, I tell you, this is definitely not intuitive. So this was a nice experiment. So what you get is always something that is in the direction of observation of the SAR sensor, which is also called line of sight. So we get a beta, even not exactly, but we will see that. What we get is something proportional to the beta. So this is what SAR measures, but it might be useful to also get the sigma, which I already told you, this is proportional to physical parameters of the observed target. In some cases, when you really want to get totally independent from the geometry that you use for the acquisition, then you can use the gamma. We will use this, we will see this, how images look like in these three cases. So one more thing I want to say, which is one level of difficulty that comes on top, that you can do these things by using nominal values of your incidence angle, by simply modeling the Earth as an ellipsoid, or you can use a digital elevation model to understand exactly what was the surface that you were imaging. Okay? So we will always need to understand, okay, this was radiometric corrected with respect to what reference, okay? So here is just to show you that if we have a slope, then we should take into consideration, and I will show you later this transformation. So this is the ellipsoid or the digital elevation model. So this variation, this slope. What do we get once we download Sentinel-1 data? I told you the beta, but it's not exactly the one. So the one of you that have experience with Sentinel-1 data, how is this called from ESA, from the ground segment? Please. Mm-hmm. Mm-hmm. Okay. So the suggestion was more related, what is the data format? The question is not this one. I will answer it. So what you get, every pixel is a digital number. So this is what SAR is measuring. And then, but I told you the beta, it's basically the same thing. It's just that we normalize for a given area that is basically the resolution cell of the SAR. So the slant range resolution multiplied by the azimuth resolution. And digital number and beta, they look exactly the same. It's just a scaling factor. So again, it's just a matter of understanding what you download from those data. Otherwise, you get a beta. This area here doesn't depend on the local incidence angle, doesn't depend on the geometry. The other ones, instead, are obtained through compensation of the local incidence angle. So the sigma, you will get how the target is scattering in the way you were seeing it. The gamma will basically bring you almost 100% independence from your geometry. So again, for these numbers here are in Sentinel data. So you get them and you can compute everything you want. So from Sentinel data, you can, from Snap, you can automatically get the beta, the sigma, and the gamma. Just one thing you should keep in mind. These areas here do not take account a digital elevation model, but they simply consider the ellipsoid, okay? So when you really want to compensate radiometrically your data, then you should do it with an external DEM. Let's look at some images to be more clear. So here we have a sigma node where we have no terrain flattening, so no radiometric correction, no terrain correction. Then we apply the terrain correction, and what we see is that already this slope here, we can notice, gets spread on a much larger area. So here it's clear what is happening. So these shorter slopes, we are really stretching them on the actual dimension they would have looked like in a optical image. What if we apply also terrain flattening? Here comes the difference between the sigma and the gamma. They look more or less the same, but you can see that in the sigma, you still see some variation due to topography. The gamma, it really looks like, okay, we cannot recognize any topography in our data, okay? So since you, more than questions, you would like to have answers, I put here this table here. So when to use what, because this is not straight to answer. So the beta, we said, is computed without considering the local incidence angle. So it is the most general term. It doesn't vary with the incidence angle. And the nice part, it doesn't need a digital elevation model to be computed. So if you don't have, it's not a big issue. So high resolution digital elevation model are not that common. Of course, you could use the 30 meters Copernicus DEM, but still. Contrast, something that we don't like is that it may vary a lot due to the geometry. Of course, we didn't compensate it, but this can still be useful. So when you don't have any knowledge of the scene topography, it can be used, or when the local incidence angle is something you want to understand from your data. So don't compensate it if you have some dependency on the local incidence angle and you want to know your geometry, don't compensate your data for it. So you can use the beta. Or, for example, the satellite system has few look angle option, because there was a question in the first part of the tutorial. What do we do? Do we compensate for it or not? Does machine learning do the job? Well, Sentinel-1 use one look angle for interferometric wide swath data. If you get TerraSAR-X, you have, I believe, 7 different possibilities of look angles, so of geometries. And this comes on top to the digital elevation model. So it might be the changing sensors, then you might need to always take into consideration one parameter or the other. So otherwise, we said the sigma as a physical meaning, nicest parameter if you want to invert scene parameters. I want to do land cover classification. I want to understand how my land cover is behaving on different local incidence angle. One thing here just don't forget to feed the incidence angle to your machine learning algorithm. So it's not that you are getting 100% independent from the geometry. You will need still to tell the algorithm, look, that I apply this and this is what I obtained under given circumstances. The last one, as I said, is the most general one and one that is supposed to be most independent on the geometry. And of course, what is nice here is that if we want to compare between different sensors or different geometries, this is the one that allows you to get the most independence on the geometry. So sensor independent target characterization, or also yeah, mainly this. So different sensor could also be combined better with the gamma. Is there any question about this table? Please.
One question, when we order or pass SLC data versus QRT data, that sigma will be delivered for the SLC data, right? Not the median values then.
So the question is, what is the difference when we get SLC data or GRD? What is that we are getting if we are getting the sigma? So the SLC, when you download them, you get beta, as I showed you before. The GRD, I believe, the Copernicus browser will provide you with the same, with the beta. But if you download your data from the Google Earth engine, they provide the sigma. So GRD doesn't mean much if you don't see what pre-processing was done to those data. Okay. Any other question? Please.
What about, I don't know if you ever worked with Planetary, Microsoft Planetary. What about the catalog with the RTC correction? Which kind of value, it's different from these three ones, yeah? I mean, we talked about domain terrain correction. Is it correct to work, for example, sticking Sentinel-1 and Sentinel-2 using, for example, Sentinel-2 level 2A and Sentinel-1 RTC sticking it before the learning part?
So the question is, by using Microsoft Planetary, this is the right name?
The RTC version.
So RTC data downloaded from there. So I don't have experience with the specific data that. So let me give first a general answer to this. Probably then we can see more specific what it is. So when you talk about RTC, the only two difference that you can get is if the incidence angle used in the formulas were taken from the ellipsoid or from a digital elevation model. I guess this is everything related to the ellipsoid. Yeah. So if you can then align them together, I guess so. You should know that correction you made, it's only related to the ellipsoid. So just roughly speaking, you will not see like the ellipsoid just corrects this intensity, the brightness at the border of your images. When you stick them together, you will not see any more stripes, but everything will look more homogeneous. But on the mountains, then you will still see these variations, okay? Welcome. Okay, so the last part before proceeding with the snap processing is about the signal properties. I will go fast here. So it was said already before that we had this speckle effect. I just want to mention here that we have different types of scatterers. We classify mainly in three different types. So we can have distributed scatterers. So let's say we have a ground, a bare ground, or a vegetated ground that several pixels look the same, adjacent pixel. Extended target might be man-made structures like urban scenarios. We can have buildings. Point targets are something which also could come from buildings, but these are corners that have a level of scattering very, very high due to their shape mainly. And so this will affect how the image will look like, but will also affect the statistical description of our image. Usually, for distributed scatterers, we can say that we have so many scatterers in one single resolution cell that we collect them all together coherently, because the SAR is a coherent measurement. So we sum them up, not simply the intensity, but we sum them up coherently. So we should consider the direction that the single scatterers have in the complex plane. So this can happen that a uniform target that for us look the same in optical image will look like a forest or just a bare ground, will look everything brown. We will have that due to the fact that we have different scatterers in the same resolution cell, will look differently bright. So some pixels will look very dark, some other very bright. This is described as salt and pepper noise, and this is also called speckle, which is pseudo noise because actually we know that this would be information. If we would be able to describe these single scatterers, then we would also not have noise, okay? So I recall this is the same slide you have seen before. So you take a uniform area, the noise looks like this, and then you have, for the amplitude, you have a gamma distribution. I also provide a Jupyter notebook where you can play with this. You have different targets, and then you can observe from the histogram, we have somehow an empirical probability density function where you can simply change the patches and then see how these different data are distributed. So, data preparation, I mentioned Snap many times. This is a free and open software provided from ESA. Through Snap, you can do all the processing we have spoken about, and I can give you a very brief introduction to that. The interface looks like this. All the main commands are basically on these bars. Very interesting is the graphs option, where you could create your block scheme, so you visualize your processing and basically perform all the processing through graphs. Data results are got here. Here we visualize them. Let's start immediately because we don't have that much time. So I downloaded and pre-processed some data just to show you how then data looks like. So I guess this was, the data was pre-processing. So when you download the data, you can just load them on Snap, and you can have some preview of the data. You get quick looks here, but for example, let's see what bands you get as input. I told you, you get 3 different subswats. So it's like that you get 3 different data. I and Q are basically in phase and quadrature. So this is the name. So it's basically real and imaginary part of your complex data. Then you get the intensity. You could compute from them, but they provide it here as well. So Snap provides here. And then you get 2 different polarization with VVH and 3 different subswats. So in total, it's like 6 different data. Let's visualize one intensity. We should not push Snap too much to do what we want. Okay, so this is what we get when we visualize the data. And of course, we will not be happy. It doesn't look that nice. So we cannot really look into the data. This is just one subswat. We could try here to modify it, to transform it from linear to dB. Still, it will not look that good. First, we should do some other operation. And one operation is we go, for example, we can take rather here the graph builder, or we go on radar. We go on SAR utilities. You can play a bit around with these things. No, the very first thing will be the depth bursting. We look for graphs, radar, standard graphs, and then we have multi-looking, orthorectify. This is the geocoding, the orthorectify. This is the transformation from single look complex to GRD. Where will I find the depth bursting? So for Sentinel-1, we have a dedicated set of operations. So always look first in the Sentinel-1 tops. And basically, so what we have here is the conversion to GRD. We have, some internal operations. So this it splits different subswats. So if you don't want to process them all. So here is the depth burst. So if we select depth burst, it's basically creating the processing for us. I will not, so it needs always some time, so I pre-process the data. So I will, I will show you now how, for example, depth burst data and terrain correct data look like. This was... So if we get a single intensity, so this is related to the VH polarization, and we have that those stripes will not appear anymore. The depth bursting here is meant for mosaicing as well. So you will you will put together the different bursts and also the different subswats, and then this is still in the SAR geometry. What you can do, it's what we visualized before, is applying also the terrain correction, and then it will look like this one. Then, of course, you can apply multi-looking, transform into dB to see better your data. And all the tools that you will need are basically here in radar, Sentinel-1 tops, or you could also play around with graphs, where you get radar tools, and mainly everything will be in standard graphs, like the orthorectification. If you go inside, it's called the terrain correction, so it's basically our geocoding. Just a second. So if you go here, in the terrain correction, you could also apply the flattening. So if you ask to apply radiometric normalization, then you can ask to save the sigma node, gamma node, or beta node. Not to this type of data, but basically the one just after the bursting, okay? So if you have any question about SNAP, we can see this. This is mainly, you will need some practice to play around with the option, but here there is basically all the processing you will need. So very soon there is an archaeological visit, very nice one, 2.5 hours, starting at 5, at the Arch of Traiano. But before...
We have 5 minutes to reach the Arch of Traiano because someone is going to steal the arch
Okay.
and to move it in another place. So you have 2-3 minutes to say what
So
you
I will wrap up in 2 minutes. There is another thing that I would like to... So there is the third part of the presentation, which is done through... Nice. This was...
You will share all this presentation.
Exactly. What I want to mention is that I will also share a Jupyter notebook, and I wanted to simply show to you what is in this Jupyter notebook. Basically, what we saw so far is how to create our data, but what we want to know is how do we normalize the data for machine learning. Okay, we apply log transformation, and then here starts the trouble. So how I do this properly, what it makes sense or not, and at the end, what I should take care about in log transformed data. I provide you this type of data, this image here over San Francisco, plus already NPY of these other data. So you don't need to crop the data by yourself, and the Jupyter notebook is self-explainable. So you will read the text I put there, and then of course we can text. So just to wrap up, this stuff is definitely just examples. Just the takeaways, you will need a lot of domain knowledge in SAR to apply machine learning. These are considerations we already made through the presentation. Thank you very much for participating so actively.